everyone. We're going to get started with our next speaker, Daisy Zhuo. Daisy Zhuo is a co-founding partner at Interpretable AI. During her PhD in operations research at MIT, she developed a range of cutting-edge machine learning techniques such as optimal imputation and robust classification, which have become the core software modules of Interpretable AI. With expertise in mixed integer optimization and machine learning, she continues to develop and apply new machine learning algorithms at Interpretable AI. Please welcome Daisy.
Thank you very much. Yeah, first of all, thank you very much for having me. And I have to apologize for the mask. I have a 2-month-old at home, so just want to be a little on the cautious side. So if you can't hear me very clearly, if I'm mumbling, just raise your hand and I will, try to speak up. But you can hear me all right now, right? Okay, great. Thank you very much. Yeah, so today's topic, I wanted to kind of just share with you some of the stories from, the collaborations that we've had with the Fortune 500 companies or smaller companies of them trying to start AI projects, whether on their own or in collaborations with us. What works and what doesn't work? What are some of the, really roadblocks of making an AI project success? And how do we avoid these failure modes? So basically, I will talk about some of the implementation risk going from problem definition to data issues such as bias and data quality to some of the specific things that you can take to manage these risks. So a little bit background about my company, Interpretable AI. So we started with the Professor Dimitris Bertsimas and another classmate of mine out of MIT's Operations Research Center. So we did a lot of research with the Professor Bertsimas there in terms of coming up with new methodology that can help businesses understand the AI system rather than just trusting a black box model. So we had a lot of interest in our software or in our algorithm back then, and we decided, hey, why not commercialize it and actually help companies build solutions that they can trust in the end. So we've been around for 4 years now, and we have several modules that goes from data cleaning to predictions to prescriptions, and then you can see some of the these methods in application when I talk through some cases. So far, we have worked in a variety of industries from healthcare, which is one of the key motivations for Dimitris personally and also for us all together to help doctors not only just trust AI blindly, but actually see what's going on so that they can actually improve their decision-making process to finance, to insurance, to manufacturing. All right, so coming to the topic today, again, we have seen that companies have been investing very heavily in AI, in data for many years, but still there's a lot of them that are just failing to extract the values out of it, right? Like the projects either fail or even if it gets deployed, the value might just not be there in the end. Nobody is using it. So we wanted to get down to the root cause of it and see, AI has uncertainties. We all know that the models are not 100% correct. But what are some organizational and operational things that we can do to minimize these risks? So Google, actually, there was a bunch of researchers there that decided to tackle this problem or to investigate this problem themselves. So they interviewed, I think, 40 key data science managers that are involved with high-stake problems. And they said, okay, let's look at this whole life cycle of a data science process, starting from defining the problem, data collection, and all of the model building, all of the, the fun parts where you go play around with your deep neural network, all the way to the deployment. And what they found, and we've seen that over and over again in our practice, is that most of these things fail at the end, but not because of this last link, but actually from mistakes or issues way early on. So again, they coined this concept called the data cascades, and they say that 92% of these issues come from the issues of not having the right data, not having a good quality of data, the problem and the data don't match up. So let's kind of think about this in a little bit more kind of detailed way. What's going wrong with the data? Is it because you just were not able to collect the data like as you kind of set forth to do. That's not always the case. It's actually even earlier on when you're trying to find, like there's the product market fit, and here we have the problem and data and method fit. And if anywhere in your, like the triangle of the problem, method, and data is not perfect there, then in the end you're going to build something, but the thing that you build is just not going to solve the final problem. So to put it in like a positive note, I wanted to share a few cases that worked really well for us, that we had the model go all the way from the beginning to the deployment, and then I turn around and look at some of the failure modes. So the first one was with a real estate platform company. You can think of it as a Zillow, but they actually do transactions there. And they came to us and they said, hey, like we want to increase our sales, we want to increase our revenue, but our pricing model is not great. We're just using these AVMs, which are based on, comps or based on some neighborhood sales. It doesn't actually take into account of like the trends in the market. And so working together, their hypothesis is that on their platform, there's actually a lot of signals, things like people clicking and saving places or just simply viewing the places. So we started working together to build a model that used these signals to really like capture the dynamic market aspect, and then use that to make predictions that are better than a simple AVM model. So we worked very closely with the COO, who was a really strong believer of this, mission of using this market signal. And together we built this optimal decision tree, which you might not be able to see very clearly, but basically based on, again, this is an example, but if it's a first sale on the platform, if the interior condition is good or bad, and the number of bedroom, bathrooms, then we can come up with a probability of sale for any given price. So now combining this predictive model that incorporates the real market signal and the pricing, the range of hypothetical prices, we can run some optimization model and help them decide what is the best price to set. So we ran a pilot trial with them, which resulted in 18% additional sales and some additional revenue, and that was rolled out kind of at a larger scale where these numbers continue to translate into real value for them. So kind of thinking back about this project, what made it really work, we think, is three things. The first is the stakeholder involvement. So again, the COO herself is very invested in the project herself. It's kind of her idea, and she really wanted to make it work. So at every meeting she was there, she always works very closely with the salespeople or end users or us to like really understand what's going on, and very critical, obviously, when things go wrong. So I think, these projects should, obviously there are a lot of good projects coming from the bottom up, but you also want to have the involvement from the real stakeholder and the real users from the very beginning, because what you really want to avoid is that in the end someone comes to it and say, hey, this is not interesting to me, or I'm not going to trust the model. The second one is the kind of a translator role. So a lot of times we find there's some disconnect between the data science group and the end user or the business people. And it's very important for someone who can speak both language so that they can actually convey the model to the people who are going to use it. And in this case, we had this gentleman who is from a more business background, but super keen on just learning about, what's a false positive rate, what's an interpretable model. So all of these kind of, not in the nitty-gritty, but like still a very important conceptual level of these models, so that he can say, now what has changed, what we sacrificed in exchange for, so that he can actually tell the people now, the decision makers, that, for their benefit, what is really being updated or changed from iteration to iteration. Because oftentimes in the end you're just saying, oh, our accuracy went from 90% to 95%, but it doesn't actually mean much to someone who is going to spend his money on the project. Great. So the third one is the feedback from users. We had salespeople who were using these platforms for the pricing, and they were really helpful because the initial rollout, we had them review these pricing decisions, things like, hey, like, do you agree with each of these splits, and does that make sense to you? And sometimes they do tell us, hey, this is not intuitive, we need to revisit it. So by taking these expert input or their interest or what works for them, what doesn't work for them, would actually help us a lot with getting better data and improving the model from round to round. Make sense so far? Great. So the next example I want to talk about is with a insurance data company. So they were suffering a lot from like the data quality issues, and we all know insurance data is like super messy, right? And one of the specific problem is that they need to, for example, if they want to predict someone's spending, medical spending next month, then they need to know what happened to that person. The issue is that, in this claim from this hospital and that claim from that pharmacy, they're not necessarily linked together nicely. So an example for myself, maybe there's a typo in the name, maybe there's a SSN with some dummy values, maybe there's a swap in the date of birth. So when that happens, how do we know that that is me, and how do we clean up the data so that it actually makes most sense? So working together with them, we again came up with a interpretable decision tree that based on some features, and that was able to separating out people who are actually the same person, people who are not, with very, very high accuracy. So this problem worked really well. We think the first thing is that the problem is actually very well scoped. So we didn't just come out and say, we want to solve all of your data quality problem. We want to, clean your data so that all your predictions are going to be perfect. We know that, this is a problem that what's your input, what's the output that you desire, and you have a quite nice way to collect the data. So this is very, very simple because what you don't want to go into is that keep changing your goalpost for your data scientists. One thing is that then it oftentimes won't work, and it also hurts morale, right? Like your data scientists do want to work on a problem that, they have their own kind of creative input that they know, and they can see kind of the end of it rather than keep changing it. The second one is the availability to collect more data on demand. So we were very lucky that we had access to an expert who was able to, when we say, oh, the model has trouble differentiating people whose last name are the same, but the first names differ by 1 or 2 characters. So then we say, okay, can you help us to differentiate that more? Here's 100 examples that we want you to help us label. So having access to that is great because now you can dynamically, really efficiently collect more data rather than just trusting sort of a random set of data that may not be actually really relevant to the end task that you're having. And the third one is a clearly defined metric. So, like if you took these classes, you learn about F1 score or AUC or accuracy. But what's important here is that we knew what is the important metric here for the business application. So, for example, you don't actually want people to be two different people to be considered as the same person, right? And alternatively, you also don't want the same person to be considered as 2 different people. But the issue that incur with these 2 scenarios are different, and some of the cost of wrongly putting 2 people together might be higher than the other. So depending on your application, you actually do want to think very clearly what is the real metric that's going to affect your business in the end. So coming back to this problem, if we see that everything kind of happens at the beginning, how do we kind of manage these problems? How do we first identify these problems, right? Like see before they even manifest, and then also what actions can we take to avoid these problems? Do we just abandon the project altogether, or do we kind of revisit the data collection process or revisit the problem definition phase? So Let me now go through each of these failure modes in that process and talk about one by one how to avoid them. So in terms of the problem identification, so first of all, I kind of separate it into three major categories. One of them is in the problem definition. That's the foremost important part where you really want to make sure your data, method, and problem has a good fit. And if you don't do that well, that's that's just going to be bad. The second part is in the data collection process. What are some issues with the data? Is there going to be bias? Is there going to be sample size limitation? And finally, there's this translation from POC to the wider adoption. Say, everything went perfectly. Your POC shows a 20% increase in whatever, but sometimes the projects still fail because when you're kind of making that last step, that's when the translation didn't happen. So how do you find some early signals of that and avoid it? So in the problem definition one, the first thing I think is kind of choosing the wrong technology for your problem, right? Nowadays, everyone talks about deep learning. Your vendors are trying to sell you that. Your data scientists really want to build the next BERT or AlphaGo model for your machine, but is that really going to solve the problem, right? So just take deep learning as an example. There's a lot of requirements actually for it to work as promised. You're going to need a lot of data, and that's just not just thousands, but actually orders of magnitudes higher. It depends on the format of your data, right? If you're looking at language or looking at vision, maybe that is the state of the art. But for tabular data, there's actually a ton of research showing things like random forest or XGBoost that can just do as well. So maybe you don't have the right format of data. And then I think more importantly, does your model require interpretability, right? If you are developing the next long approval process, and you need to show the regulators that you're not discriminating against women, against the elderly people, then deep learning might not cut it. So at that point, if you ask these questions and then answer them one by one, maybe you can figure out, okay, that's not the right model for me. So I'm going to think about another model, and if that model doesn't work, maybe we should revisit everything. Another one is about I don't know if, I think, Catherine, you mentioned there was already some talks about prescriptive versus predictive data-driven decision-making. One thing we've seen over and over again is that the problem itself is actually prescriptive rather than predictive. So here is a company that we worked with where they wanted to make a pricing decision for their car sales. But so for them, okay, they worked with another vendor. It was very easy to build a gradient boosted model to predict to predict sales based on the price. But the real problem is actually finding the causal relationship between the discount or the price and the sales, right? So you could have something that predicts pretty well, but because everything is correlated, you're actually not getting the real relationship out. So you could be inflating the effect of discount, or you could be discounting it. So whatever comes out of your model is actually not sufficient for you to make that causal inference. So in the end, if you actually make your pricing decision accordingly, you might actually hurt your business. You might lose more sales. You might lose, some of the intended effect. So that's one problem. And for this one, we worked with them using this thing called from the causal inference literature and using optimal policy trees, so that we actually kind of treated with a very rigorous causal perspective to isolate what is kind of the predictive background noise and what is actually the causal aspect, so that we isolate that as much as possible out of the story. The second one we think is in terms of overestimating the value at stake. So a lot of times, someone would think the market is really large. We're going to have this number of users that's going to, be affected by our new pricing model, and we're going to have this and that. But if you combine that with your data availability and your user who's actually going to be exposed to your new, a strategy, it might actually be smaller than that. So take that real estate company as an example. We worked very well on the first project, so they wanted to do a follow-up project with us. And the idea is, okay, we're going to do a recommender system similar to Netflix and tell people, hey, given these houses you saw, we're going to think these houses that you will like. And they estimated that everybody is going to, to want to buy 20% more houses. But what turned out is that we actually have a lot fewer users that have the data that would allow us to do it. So I'm not going to go into details, but some users don't log in. Some users actually create fake accounts to avoid this kind of tracking activity. So we estimate in the end there was only a third of the users that might potentially, we would be benefiting from it. So in the end, we decided it was not worth the investment to do. But again, just the lesson that not all of your users are actually going to create the value you have in mind. The third one is unrealistic expectation of performance. And this one, I feel it's actually particularly interesting nowadays because, we say, okay, AI is going to affect every aspect of your life. The models are getting so good, they're almost at 100% accuracy. But the problem is, as long as the model makes even a single mistake, there are some cases just it's not going to be acceptable by the user. So in legal industry, for example, you actually have to pick out every single clause correctly. Otherwise, it may not fly in areas like healthcare or in fraud detection. So this is something that you want to first really be aligned with the user, right? So even a number like 99.5% just may not work in that use case. And we had an example where one of the cybersecurity firms, first their whole thing is about using AI to detect the malware, compared to, in the past, most of these detection tools were using rule-based approaches. And their model was great. They had 99.5% accuracy. But one time, it just broke. It was way worse, and they had no idea what's going on. And that raised a lot of concerns and uncertainty within the firm. So we came to them and helped use some of the interpretable technologies to dissect what specific cohort and areas of activities that have a significant drop in performance. And that was very helpful for them to improve. But overall, I think for them to even to make that decision of an AI-based approach that's highly accurate to solving that problem, they have to think through, would they be able to tolerate when things go wrong? So another one, I think it's kind of relevant to the first one, but it's about misunderstanding stakeholder appetite. And this happens a lot, when you think, the doctors would love my deep learning-based method, but in the end, we've seen over and over again, they just point at the paper and say, what is this? I want to be able to see how you make the decision. So again, that's something important to do early on. The next part is data collection. I think this one is interesting. If you have a lot of data, you might think, okay, this is, perfect. I can really build a good model on it. But the big data doesn't really mean you have good data, right? One of the examples we did with the car manufacturers is that we wanted to predict the machine failure. And they have, I think, tens of thousands, if not hundreds of thousands of IoT device tracking data. And they also claim they have nice labels on when these devices failed. But when we looked closer on these log data of when the devices failed, it turned out it was 80% log of whether the door opened or shut. So it was very much inflated with these noises that have nothing to do with the actual outcome that they have in mind of predicting. So when we trained the model, it was picking up a lot of noises, and it wasn't at the level of accuracy that they have desired. So we think that's a very important thing to, at first, to know the quality of data and whether it fits your use case or not. The next one is about the data size. So again, it seems very intuitive and obvious that you need a lot of data. but sometimes it doesn't actually register. And we've seen over and over again when people are trying to make time series predictions, but they only have quarterly data from the past 5 years, or when people are trying to learn what makes a big event successful or unsuccessful, but they only have a handful of events to learn from. Oftentimes, machine learning is not going to do anything better than a human expert-based method or a time series method. There's the bias in the data collection problem, and the bias is not just in kind of the ethical bias, which is a very important part, but even in things like manufacturing, you want to make sure that the data you're collecting follows exactly the same kind of a split or the mix that you're going to see in your deployment. So I skip through some of the examples. I know we're a little short on time, but just to talk about some of the final step, like how do you make that final leap from the POC to a wider adoption successful? The first thing is that this generalization issue, you have to really think about it from very early on. So a lot of times, like your model looks great in validation, even in testing, but then when you're actually deploying it, you're like, oh, like I'm actually deploying it on a mix with way more women than men, and the performance is completely different. So that's something you have to think about very early on. The other thing is about the evaluation being representative. And again, it talks about the metric, right? Your evaluation could be on accuracy the whole time that you are training your model. But then in the end, all they really care about is true positives, which can be very different from your model to model. And finally, about, like if you have built a successful POC, do you want to use the same group, whether it's a vendor or an internal group, or do you want to actually kind of rebuild it to reduce the cost? And this, again, depends a lot. So we have a story where we worked with a company with a POC, but they swapped it out with some open source method. In the end, the performance gap really kind of prevented the project from really taking over there. So a lot of things to think about, like what is really at the point when they're deciding, is it just scaling, or does it involve kind of, the human aspect, because that can actually be make or break that transition. So to wrap it up, I think, like obviously this is not going to be a very smooth process. Even if you do everything perfectly here in the whole step, your model still might not be deployed, and we all know about that risk. But the best we can do is to kind of keep that in mind every time we make a major decision, whether to acquire data or whether to do this project or not, is to have the end goal in mind, so that if that connection is there and if your evaluation is fair and correct. So a few things I have just kind of summarized here. In terms of people, you want to have the shareholder agreement early on. You want to have someone who speaks both languages, and you want to make sure that the shareholders or the stakeholders are willing to trust the solution that you're going to present in the end. In terms of defining the problem, you really don't want to solve too big of a problem, and the more well-scoped it is, the more likely of success it's going to be. And again, the metric, you want to define it at the early stage so that you know that it will translate to whatever the end is. And then on the data, initial assessment of the signal level rather than just simply looking at the number of observations is key. And finally, if you have the capability to dynamically collect more data, that's going to be a lot more helpful than just having a dump the CSV and think good luck that you're going to make the best out of it. So with that, thank you very much. Let's take any questions.
Yeah, great talk.
Thank you.
So you were talking about where if the problem or the solution is not generalizable,
Mm-hmm.
right? Do you find it useful to find those not generalizable solutions and then say, okay, we'll just funnel this subset into the algorithm that still works and solve it piece by piece? Or do you feel like zooming out and saying, okay, we need a general solution that's single solution is the right way?
Yeah, good question. I think it, again, really depends on the scenario and depends on how similar the non-generalizabilities are, right? So, for example, in the case of, trying to think, in the case of finding, let's say, finding why a machine failed and it worked in this plant but not in another few plants. If you look at the issues with why it didn't work in the other plants, if it's systematically because a certain signal wasn't collected, or if it was completely a different scale, if there's something that's similar, then I think kind of taking kind of a more global view to resolve that difference is the better approach. But if each one of them has their own characteristics, so for example, Germany is very different from England and from this other place, then, and that's, there's nothing really shared among them, then perhaps you do need to make kind of a specific funnel per market and do it separately. Thank you.
You showed a lot of decision trees as examples. Which models do you find to be the most interpretable by your customers, and then which are the least? I think I know the answer to least, but I wonder which ones are most.
Yeah, so if I understand it correctly, and I assume you have some kind of background with there's card-based decision trees, there's some other algorithms, there's the most recent one that came out of my colleague Dimitri's and Jack's work called optimal decision trees, where compared to the previous ones, not only it's I think like 4 or 5, maybe 3 or 4% better in terms of performance, it also is actually smaller in a lot of the scenarios. It reduces the false selection of signals that just shouldn't be there. So in the case where we're limited to decision trees, the optimal decision trees do kind of actually thrive in interpretability as well. And then if you look broader, obviously there's a random forest and XGBoost that are some combination of decision trees that are much more difficult to interpret. Mm-hmm. Yeah. So linear regression and logistic regression, if you have a reasonable number of variables that are selected in the end, they will be very interpretable. The issue is that sometimes you end up selecting way more than necessary. So in the case of, there was a medical predictive tool that was used in the market that needed 20 or so variables. And even 20 was actually a lot for the doctors, because for every patient, they had to answer every single question. So we ended up making a decision tree that only needed 5 to 7 questions. So again, I think that kind of scale would also dominate how interpretable methods are. Thank you.
You mentioned that after the proof of concept, that companies would choose a different solution.
Mm-hmm.
Could you speak a little bit more what motivated that? Was the proof of concept not scalable? It seems ill-advised to not follow proof of concept.
Yeah, we were a little surprised too. I think a lot of it is, one thing is obviously budget and cost. There are some, if it was built with a vendor, there is some cost issues, but also they want to build up their internal data science department, right? They just hired a lot of people. They really wanted these guys to take the ideas and build it themselves, even though some of the underlying technologies could be different. They believed it's more, like if we kind of upscale our own data science group, we can overcome the differences in the underlying models. So I think the combination of, if we can both cut costs and make our people smarter and probably still build the same quality product, why not give that a try? And in this case, it didn't work as well, and that's why it kind of failed. Thank you.
Do you have any advice on how to make a neural network solution more interpretable?
Yeah, there's a ton of people working on it, and I wish I had a good answer for you. I think there are ways to explain a neural network, right? After you have it, you can run some kind of sensitivity analysis, things like SHAP or things like LIME that at least tells you how the result varies with certain variable inputs. The sad thing is you still cannot inspect them yourselves. There are ways to reduce the complexity of neural networks from billions of parameters to hundreds of millions or tens of millions of parameters. But once you're above something like 10 or 20, then there's really no hope for a full-on interpretability compared to a tree where you can actually see and play around with. I hope that's helpful.
A couple questions, one hard one easy. On the data block there, sufficient signal and dynamic collection. So I'll start with the easy question. How do you decide, or is there a framework for deciding where to collect additional data if you don't have enough signal? Mm-hmm. That's probably the easier question. The harder question is, how do you decide what additional vectors to add to your data set if you don't have sufficient signal?
Oh, great questions. So the easy one, some of the ways you can do it is, so for example, if we have a thing like a decision tree, and you can use it, some other technologies with it too, but say in this particular cohort of, say, houses or, cars, the model is just having a lot of trouble differentiating that your accuracy in that particular node is very bad. Then you know that's going to be your next area of collection. So we're actually working right now with a company to figure out, we're collecting data on farms through a North African country, and we're trying to see how well the model is going to predict the quality of soil and their production there. The thing is, right now we don't really know where to collect data, right? It's really like a blank, just starting from scratch. We don't have any data to start with. So there's actually a way for you to build a whole dynamic data collection process where you first have some kind of scattered sampling to start your process. Then you train an initial model, figure out where the model is having more confusions, and then start having more dense data collection in those areas. So I hope that answers your first question. And the second one, I think expert input is super important in terms of coming up with the right vectors. So with these healthcare cases, we constantly ask these doctors, so in addition to ventilator status and BMI and age, what else do you think is making a person much more likely to have a morbidity after surgery? And sometimes it's in their mind. You just have to kind of get it out and also figure out if it's easy to collect. Once you collect that data, then you can iterate and then work out with a more refined set of signals. Cool.
My question is on the operational aspects of AI. When you deploy these models, and in the case of the cybersecurity firm, where the models start failing, how do enterprises build operational resiliency to handle such scenarios? We've seen the case with Zillow. It's lost almost 70% of its valuation, presumably for the failed AI models.
Yeah, I think that, again, is something that there's not an easy and clear answer, but you can try to catch it early and to have some warning signs before something fails like that, right? So for example, with the cybersecurity one, if you have, some kind of a constant alert system ahead of time, or even just with a small subset of the samples as they're coming in, and you're already seeing certain deteriorating behavior, and then have, build up some quick solutions, or whether to warn the users, or, again, it depends on the industry and the application, that will at least help with some of the operational aspect. I do think to kind of automate that and to make it much more robust, that requires, a whole other area of research to make that work. Great question. Anything else?
Is the optimal, sorry.
Is the optimal decision tree policy that you guys talked about, that's your like proprietary kind of methodology for producing these kinds of trees, right?
Yeah. So like going back to our kind of set of products, optimal decision tree is and the predictive one is sort of the very core and the beginning of our set of technologies. But I think so we've also built on top of it things like optimal policy trees or optimal prescriptive trees that. So in this set, that kind of build on top of this way where you train really good decision trees, but for different tasks. Another one is feature selection. So it goes to your comment on regression. So it actually is solving that regression problem, but finds you a smaller and the best subset of variables. So it's even more interpretable, but probably has like a higher accuracy as well. So that's also came out of our group's research. Great.
Awesome. Thank you, Daisy.
Thank you very much.